everyone, and welcome back to the Information Bottleneck podcast. And today we have a very special guest, Will Brown. Hey, Will.
Hey, how's it going? Thanks for having me.
Thank you. And hey, Alan. How are you?
Hi, Ravid. Hi, Will. It's a pleasure to be here again.
Yeah, so today we'll talk with Will, and he's like the expert in reinforcement learning, and we'll talk about what he's doing, what he's working on, the RL frameworks that he's developing right now. But I want to start at the beginning. Maybe tell us a bit about yourself, about your path to the current role.
Yeah, absolutely. So, I think if we want to go way back, I've always been like into math and computer science growing up. And then I think also had an interest in like more conceptual, like I was really into like debate as a kid too. And then I think like in college, I got very into like both computer science and philosophy, and was originally like imagining I would just go be a software engineer because that's what everyone else was doing. Is you study computer science, you think about programming and building systems, and then you go work at some tech company. And like I did the internships, but the things that always were the most exciting to me were like the algorithmic angles of it, the math pieces. And this is like very early like data science days when like the machine learning was like becoming more prominent for people. Like 2015 or so, when it was like more of a focus of like deep learning was happening, but we didn't really have anything look like modern AI yet. It was like very kind of nascent in terms of large scale applications being useful. And so as like undergrad progressed, I was definitely like thinking a lot about like, okay, what is the most interesting stuff to work on here? And it was clear that it was some sort of like learning systems, something algorithmic. And I got really into the idea of like multi-agent systems, and especially like learning in multi-agent systems and thinking like, okay, self-driving cars were like starting to happen. People were thinking about like, okay, what is this going to look like? Then you see like AlphaGo happen and the early days of RL for like Atari. And at this time, I was like really deep in the theory side. My favorite classes in undergrad were the theory classes, and I really liked proving theorems and like designing algorithms. I liked the programming too, but it felt like the programming that people were doing was less inspiring. It was like, oh, we're going to make a better web scale stuff, which is like cool, but it was like, it didn't feel like the frontier of some like massive challenge, as opposed to like, I think it felt like AI and machine learning theory at the time was a way of like peeking into the future of seeing like, okay, one day this machine learning AI stuff is going to look like large scale learning systems, and how do these systems actually interact with each other? And so that was like kind of the question that I was thinking, maybe finance, but like really I got excited about doing like a PhD. And so I went and did a PhD where I was working on algorithmic game theory and multi-agent reinforcement learning, and really thinking about like, how do these systems work in long horizons over time? How do you evolve multi-agent learning systems, especially in like these many player settings outside of like zero-sum games? So like for anyone with a little bit of game theory background, like there's a lot of stuff in game theory that's really easy if you have a 2-player zero-sum game like rock, paper, scissors. A lot of stuff gets much more complicated once you have or a cooperative game can also be like a simple case where it's just multiple agents working together to like solve a problem together. But once you have like misalignment or like different, not fully cooperative or competitive objective functions for many agents, like things become much harder and much more complicated. And there was a whole world of like game theory to explore around like what happens when you have many agents learning in a setup that can be modeled as a game. And so that was really what I was like interested in. And that's what I spent most of my time in grad school, like going deep into.
But this is like, okay, so like for those of us that don't know game theory, so like, and then you have some kind of like set of assumptions, right? And now you want to, I don't know, to put them in the equations and see what is happening. This is the type of thing that you did?
So I guess for me, yeah, that's a good question. It was really trying to think about like the geometry of the problems, where like if you think of like chaos theory or like the weather, or, like all these things, there's like you can kind of visualize like, let's say there's a cloud moving somewhere where it's like, okay, the wind blows in and the cloud comes, there's this vortex that the system evolves over time. And people have developed lots of math to think about the evolution of these systems. And in a similar way, you could think about systems of people or systems of agents or systems of algorithms that have some initial conditions. They have some like momentum vectors, which could be what's the like gradient of the algorithm. So where is a step of gradient descent going to take them? What is going to go into this step of gradient descent based on like their utility function? And then now you have this like kind of chaotic system that you can set up and you can let it play forward and sort of think about like, okay, you have multiple, this is simulating like multiple players or agents in a game of some kind, where I'm using game in a very general sense to describe like any sort of like multi-agent system where different people have different utility functions, and having algorithms that there's people have all sorts of tweaks to algorithms that they do to prove different kinds of theorems, but ultimately they typically look something like gradient descent. And you should think of this as just like kind of local greedy optimization with some regularization and smoothing that are all about evolving the system forward over time based on kind of local information and objectives. And so there are a lot of, I think, interesting questions about when is this system chaotic? When is it tractable? Are there conditions where you can like say interesting things about the outcomes of these scenarios in terms of like upper or lower bounds on the like objectives and outcomes, as well as thinking about how to design algorithms that are kind of aware of this like problem geometry. So here it's like, if you're familiar with like linear programming, like you have like these polytopes that are like linear constraints on some space. And in the game theory sense, this is like some very high dimensional intangible object, but you can still use these kind of polytopes and systems of equations to characterize the boundaries of what can be reached. And you can think of this state of the world as like a point in this very high dimensional space that can be evolving over time as the algorithms evolve. And so it was really about trying to wrap my head around like, what can we even do in these like settings where there's like lots of people doing lots of stuff, because they're very intangible, they're very chaotic. But that was kind of my backdrop. And then I think as time went on, it became clear that like the world was starting to have a clearer sense of like what AI was going to look like with LLMs and ChatGPT and the current era. And I think this was sort of like towards the tail end of grad school. I was really thinking like, okay, what next? How do I take the stuff that I'd been doing from this theoretical backdrop and kind of have it mesh with reality, where reality is like, okay, people are going to start deploying these systems like tomorrow. What is relevant from the theory? What's not? And where should I be working? So I'd initially kind of thought throughout grad school, like I'll either like go be a professor, work in big tech, or be a quant. And at that time was kind of leaning in the quant direction just because it seemed fun. I mean, it was a version of this chaotic multi-agent system thing. And then
and there is a lot of money.
Yeah. But I think it was, the problem motivation was an interesting factor. And so this was like 2022, around the time ChatGPT came out, and I was deciding where to intern next. And I chose to intern at Morgan Stanley, which I think it's a research group in New York. The machine learning research team there is excellent. And it was a place where I kind of had one foot in the door from like kind of more general quant stuff, but also it was a team that was very open with their research, and they had the ability to kind of do things that were much more like nascent LLM stuff. So they had people working on like fine-tuning open models. And I knew that I needed to learn that stuff. And so it was the choice for me to go there was really about a place that I could just show up and like learn a lot on a thing that I didn't really have much experience in, that being LLMs. And so I kind of started there in like summer 23 and kind of continued for about 2 years until it was time to do the next thing. But I was doing that while finishing grad school, and it was just a really great place to like go deep on LLMs and like essentially have to learn a lot myself in terms of like actually getting these things to run, getting them to scale to multiple GPUs and like multiple nodes, and getting a very practical feel for the LLM version of AI. And then at some point it seemed like RL was going to happen eventually, multi-agent systems were going to happen eventually. And the pieces were kind of coming together of like what this vision of the old school theoretical ideas versus the more real, like practical versions of AI could look like. And that was the impetus in some ways for Verifiers, the project, as like tail end of 2024, it was becoming clear that RL was going to work, and that you could do RL for tool use agents, and that the open source ecosystem like had some missing pieces. And so I just like doubled down on that basically.
So I'm curious, you mentioned this background, it's been like game theory and even brought up some games. Growing up, got into like computer chess and algorithms for, also followed like computer Go a little bit, like what you brought up. And, I'll observe even today that a significant amount of the good performance of chess engines and modern ones, neural network powered or not, comes from just being very fast. And if you look like the neural network powered models, and even, if you look at Stockfish, if you turn off the neural net evaluation function that was added, and you compare Stockfish with no modern AI versus the very best AI stuff, it's not that like I don't know how many elo points, but it's like a few hundred. So I'm intrigued by this. I'm also just curious, how much board games you play. And I don't know, I personally really like Stratego because I think that it resists a lot of the things that computer chess kind of like, for example, like opening books and game table bases for any, you might know about some of these things, Will, but I kind of like the idea of games that in principle, a truly clever human can still beat a computer that is significantly better than it in a lot of ways due to the extreme high dimensional space in a sense. So I'm just curious. I'm just saying a whole lot of things at this point.
Yeah.
Thoughts are about all this and how it relates to your background in that transition period.
Yeah. So I think like chess is an interesting example, but I think it's kind of like the example that breaks the rule where like most games are much more complex than chess. And most games have had much less effort spent by people really studying them. And like chess is a very well understood game. Poker is a pretty well understood game. Most other games are way less understood than chess or poker in terms of people who have written books about the theory of optimal strategy and how to play them that can then be translated into kind of rule-based systems for optimizing them. And they also will have much higher dimensional observation spaces. And so the number of bits to write down a chessboard state is not that high.
Yeah,
And
and it has a nice notation as well.
yeah,
And I remember I did a tiny bit of chess programming. You can do like bit representations of that FID or whatever notation it's called. I forget the name, but there's like crazy stuff they do for this. Sorry, keep going, Will. I didn't mean to interrupt.
But
yeah. And so like I think they're like the way I thought about this like in grad school and like in the theory sense is like you can think of games as like having a fixed list of actions, but a lot of the theory actually translates pretty nicely from like discrete action settings to like bounded complexity settings where you're doing function approximation, but you're kind of making the implicit assumption that if your kind of strategy space is like complexity bounded, so like people would use things like VC dimension here, which is about, you could think of it as like the number of parameters of a neural net is roughly what it translates to. And so there's a sense in which a lot of theory can be ported over from the set of like very fixed actions and moves to like strategy spaces if you have the assumption that you can like do optimization magically. And so some of these optimization problems, like the theory is like NP hard, where you can't actually guarantee you can solve these problems. But if you kind of assume you can, and you treat like this idea of the oracle as like a piece of your building blocks, and you can have like an oracle efficient algorithm is one that you assume you have the ability to solve these like offline optimization problems for like policy spaces. To me, this was like filling the role of what gradient descent for neural networks is doing. And so like I think the hand engineering for chess is just like for example, Stockfish is like a feat of engineering. But to me, like a more interesting question is like, how do you build Stockfish for a new game without just data or with just a game representation? And so like I think like AlphaGo is kind of like or AlphaGo Zero especially is kind of the recipe there that feels more general, where yes, it's doing like infinite time scaling and Monte Carlo tree search and all these things, but these are kind of axes on a curve where you can afford to go fast because the game representation state is smaller based on the size of the neural net you can kind of afford to train at scale. And so like the sampling strategies you use, the value function methods you use, the representation complexity of the game state, these are all different axes in terms of like a paradigm of training models to solve games.
Okay, and then one quick follow-up then. So I'm a personal believer in global optimization techniques, and I'm a personal hater of gradient descent as a concept, particularly just on the grounds that, for example, in reinforcement learning, historically, it wasn't cart pull, but there's another one where you're trying to go up and down and you lose reward as you spend fuel trying to kind of get the momentum, but you hit the very top and finally you get the huge amount of reward. Naive approaches to local optimization actually really struggled on such basic types of RL problems famously. And yet, things such as genetic algorithms or simulated annealing are things that in a way relax some of the complexity or geometry assumptions. I've always felt that many of them also could have had fast GPU implementations and just didn't, kind of almost
Interesting.
like happenstance is my opinion. But what's your thought on this and in general on like global optimization, both for games and as a concept that can be applied to reinforcement learning or used alongside it versus
Yeah.
the current paradigm?
Great questions, and I have a couple different thoughts. One is like there's the whole like hardware lottery thing of like some like it could be the gradient descent one because matrix multiplication was like really important for neural nets, and so the fact that it was neural nets plus gradient descent plus GPUs resulted in gradient descent kind of being the way. I think holistically, I tend to think of these as just like two sides of the same coin. Like it's optimization, it's search. Whether it's like genetic algorithms in my mind are like a version of like 0th order optimization or like bandit optimization in some sense. But they're also like there's plenty of algorithms that you can study the theory of like what you're actually doing in terms of the sampling, where it's 0th order optimization, but the proof kind of does this reduction to gradient descent, where it's like, oh, it's stochastic gradient descent, or oh, it's like kind of gradient descent with restarts. Then there's also the like non-convex optimization literature about like these problems are so the theory fails when you have like non-convex problems. But then there's lots of kind of more heuristic ideas that I think explain why this stuff does translate in terms of like momentum and like attograd. Kind of gives you a story you can tell, as well as like it kind of explains why regularization is important and like why learning rate tuning is tricky, but like certain architectures are more favorable to it than others. Then there's like the whole muon thing of like approximating like second order optimization. And to me, it's like if you have a clean loss landscape, then and you have learning with momentum, you should expect to, and you have a rough ballpark of like what the like regularization and like condition numbers of these things are, then you can kind of have calibrate enough momentum to like get out of local optima. And to me, this is kind of what like deep learning science is all about, is like heuristically understanding what the optimization landscapes are empirically and fiddling with the knobs you have in the optimizer space to
So
like.
do you feel like the history, I don't know, the classical RL and the like, historical RL that people are doing did over the years, do you think they are relevant now? Like, do you think it's
Absolutely.
helpful?
Yeah. I mean, like, I think about, like, you can solve MDP, like discrete MDPs, you can solve with like linear optimization. And I think like the discrete or like backpropagation or backward induction, iterative approach, there's all sorts of algorithms that are like quite simple and well understood for the contrived cases or the very simple cases. And then I think you ultimately want to relax these. And so like some stuff is you have like, if you assume you have like a linear function approximator for an MDP for those who are not familiar is Markov decision process, basically the canonical setting of reinforcement learning where you have multiple states that transition from one to another based on actions, is the sort of setup that if you kind of relax the assumptions away from linearity in the same way that you can kind of relax the assumptions from like fixed discrete search or linear optimization to this nonlinear, non-convex setting where you kind of have to trust that optimization works, but you have heuristics to believe optimization maybe does work. Like it's still search over a policy space where the theory about what is a good policy, like what is a policy gradient, and like the reinforced, most algorithms people are using today essentially look like reinforced from the 90s. Like it's the same thing. It's still just optimization.
Real quick, then another question. What do you do for games that aren't perfect information? This is why I love Stratego, because you don't know what the board state is at all times. So is this, in a sense, implicit regularization? What's your take on that?
Yeah, so you can think of it as noise in one sense, but it's kind of like noise with a drift component where the noise is a function of the kind of recent behavior because it's being modeled by like potentially other players in the system whose maybe their behavior is like changing, but it's not changing instantly. It's not changing fully adversarially overnight, but it's drift. And so there's a sense in which if you can do optimization in a sufficiently regularly changing system and handle like this drift, then you can kind of like do like you're tracking the current game. And so it's a gradually changing MDP rather than a game. If you think of the other players as like regularized optimizers. And so everyone is optimizing in this regular.
Well, and I want to mind you, that it's not just that the information is imperfect, but players can choose how they deploy their armies. And their armies are quite large. By the way, I also want to advocate, I love modding Stratego. I'm sorry, I'm going to shut up.
Okay, sorry. I don't know too much about the details of Stratego, but I guess I'm thinking in a very meta sense of like, we're going to play many games, pick whatever game you want, and it's going to have imperfect information at any point. We're going to play many games, and we're each going to slightly tweak our strategy between each game. Our strategy is going to be some like map from game state to distribution of reactions and in the game, but like essentially you kind of can't update your strategy in the game because your strategy for a game is a function that maps states to actions. And whatever state you see is just like something that happened over the course of this game unfolding. And so you can kind of think of this as like, okay, how are you changing your strategy across games? And so if you fix an opponent's strategy for one game, this is just like a single player game now, because I'm now just playing something. I'm sampling. I get to pick an action. I get to observe it. I play the game forward. The deck has already been shuffled, but then it'll change tomorrow. But it'll change in a way that's kind of like based on the gradient optimizer of my opponent, which means it'll change a little bit. And so it's changing a little bit, which means I have to like chase this moving target. And so this is kind of how you get this like notion of regularity, where sometimes this blows up, but in the like 2-player zero sum case, this is essentially how like GANs, generative adversarial networks, work, is that you have this like game that both players in the game are like a big neural net that are trying to win the game. And the whole objective of this problem is to think about they're each going to change a little bit at the same time, or like alternating. And you can study the dynamics of learning in this game as they approach equilibrium. And so I think Statistical is not that different from like generative adversarial nets in that sense. If you think about this many player repeated game.
Yeah. Honestly, I agree with that analysis of it. Well, this has been really interesting. We have so many other questions for you.
Yeah. I think like we went
Okay,
through
we can get back to
into this
RL and
in this topic. Let's try to go step back and like maybe you'll tell us like about the current I know RL environments and projects that you are working on, and like maybe let's start with from the beginning, right? Like RL in LLMs, right? Like why we actually want them, why we want to do RL in LLM training.
Yeah. So
from your perspective,
I think there's a kind of a strange history of RL and LLMs where like there's been lots of false starts and lots of things that people call RL that in my mind just aren't really RL. And so like I think the thing that first caught people's attention was RLHF, which is you have a large data set of like question, answer, maybe good answer, bad answer that are labeled by humans of like, which is a better answer for a chatbot. And you use this to train a reward model. Let's say we're training the reward model offline, and this reward model is able to look at an answer and give it a score between 0 and 1. And if you think of this as a reward, one environment you could create, which is a kind of like a zero state, or there's no transition dynamics here, but I'm going to think of like the action is just simply like a sequence of LLM tokens. And so you could think of like each next token as an action, but really it's, I think, more conceptually relevant to think about each sequence of tokens as an action. Even some of the algorithms will do it at a product level, but that's kind of like semantics. And so there it's just like this input states are randomly sampled prompts. The action is do one turn of give a completion to this and then get a reward. And so this is the same setup as like the multi-arm bandit or contextual bandit problem from the theory. And it's kind of RL. It's online learning with stochastic rewards and stochastic states, but it's not. And people did use like policy gradient algorithms kind of for convenience because we had built out policy gradient algorithm like infrastructure and understanding and experimentation from like what I'll call real RL in the Atari like gym days. And so like PPO was kind of the winner of the like mind share of the like late 2010s RL experimentation efforts. And so when it became time to do reward-based optimization for LLMs, it was natural to kind of like reach for PPO because it worked, but it kind of wasn't using PPO to the full extent of PPO. It was using PPO as a like offline optimizer in the sense of you're not doing the truth. I mean, there's versions of it that kind of interplay between online and offline, but like I think especially like DPO, for example, as it was canonically introduced, was very much like an offline algorithm where it's like you have a data set, you have a set of completion pairs, and you are optimizing over this fixed data set. And there's no like new data that comes out during the process. And so I think the thing that makes something in my mind, like the two things that make it real RL is one, it has to be like online. There has to be an element of you're doing new sampling as you go. And also you want reactivity from the environment you're in, ideally beyond just like single rewards. And so I think like agents interacting with a human, this is much more like a proper RL environment. If you are simulating the human, I'm not sure that people actually were doing that in the early RLHF days. I think they were mostly just doing kind of completion answer where they like will have example data of like maybe that the input is a prefix of a conversation history, but the optimization is not planning. It's not thinking ahead about future states. And so one version of planning is this long trajectory thing. Another version is where the planning happens in token streams. So there is a sense in which, like, even though it's still like a bandit problem, doing the RLVR chain of thought RL is a little closer in my mind to this real RL, because you do have the ability to explore. You have full control over the state transitions, because the state transitions are just like, let's call them like steps of chains of thought, where it's like, what's the discrete exploration step I'm doing? And now I'm in the new state where I have done that exploration, and I can do as many of these as I want before my action. The action being something that happens after the chain of thought, is in this direction. And then I think like the agentic RL stuff, where you have tools or you have a game or a simulator, is much closer to like the whole thing, and is more like the Atari setting, where it's like, now we're in real deal RL world, where there are input states, there is an action space, there are transition dynamics, there are rewards, there are sparse rewards, there's a need to plan, there's a need to do credit assignment. And the algorithms people are using for it are not that different from the algorithms that were originally designed for this. That I think like you could still use PPO, but I think like one of the elements of PPO that was a big focal point for a lot of people for a while was this value model or critic, which you train online. And I think part of this is the idea of like people wanted to have more like native credit assignment, but I think like this seems to have kind of fallen out of fashion. Some people are sure doing it, but it seems less clear that you need it, and that sparse rewards with LLMs tend to work just fine if you have enough samples and a good enough starting prior. And so like I think the important thing that matters in like modern RL is just like calibrating. Like you want to be training the model on the right problems. And what is the right problem? The problem is one where it's going to be, you have a good chance of like getting it right, but you also have a good chance of getting it wrong. And you get information from seeing what works right and what works wrong, which at some point will essentially pinpoint like differences in model weight space or differences in the token streams, which led to good or bad outcomes. And so yeah.
What do you think like is the most important part here? Is it like that you will have like a good reward model that you will train on with a good baseline model? What do you think like when now we want to start to do our on something? Like what are the components? You know what? Let go even a bit back, like on what kind of problems we actually want to do RL.
Yeah. I mean, so earlier today, like Dorkesh Patel put out a nice little blog post that I think sums some of these things up nicely. But there's a information theoretic sense in which the optimal state of RL for potentially a binary outcome task, yes or no, is you want to be doing RL on problems where you have a 50% chance of getting it right, 50% chance of getting it wrong. And so the problem you want to be doing is a function of how good your model is. This is the complexity regime for the model where you will learn the most, and where you will need you can be the most sample efficient in terms of rollouts. But it's also a question of like, so for some tasks, it's very easy to assign rewards. For some tasks, it's very hard. And I think it's still kind of unknown the extent to which we can fully generalize RL to things we can't measure. Like in some sense, you have to be able to measure it. If you can't measure it, you don't know if you're improving. But if you can measure it, then you kind of have a roadmap towards improvement.
When you say measure it, like you mean the reward model?
It could be the reward model, but I think of it more holistically as like behaviors you want to evaluate for. So could you build a benchmark that represents, like, can I have an offline eval that I can run at the end of my training run that will tell me whether it learned the thing I wanted to or not? And to me, if the question is, if you don't know how to build that eval, then you don't know if you've done anything. If you do, then you kind of have starting to get in the direction of a reward, where the reward model often is not actually a model, but it's a system that is grading what has been done by your policy model.
So you mentioned earlier the whole 50% ideally right or wrong kind of idea. And I want to observe, I think of two things when I hear this. One of them, I think of high frequency trading, where often you have nanoseconds of time to make a decision. You know, those firms are relying on being right 50.5 or less percent of the time when they make their often very small trades. And I'm wondering if that's an ideal place. And I observe that, you know, historically there's been overrepresentation of quant firms and experts in that space, I think even in reinforcement learning, or from my observation. But I also think of just like old school methods like logistic regression as, you know, application. So I'm wondering, what are your thoughts on both of these things for?
Yeah, I think it's closer to logistic regression. Like, I think RL for quant finance is one of those like white whale problems that every quant fantasizes about working on day. I don't think it really, there are versions of it that kind of work, but the story people like to tell, and I've gone through this whole 5 stages of grief thing. I spent some time doing exactly this back in the late 2010s. Really, like, the problem is noise. Markets are incredibly noisy, and they're very evolving, and you can't really, if you could simulate the market perfectly, and as well as like the impact of a trade to really high fidelity, then you could start doing RL in it. But also, like if you can do that, there's other things you can do that are much easier. And it's simulating the market to a high enough degree of fidelity to start doing RL, especially in terms of like the way that the market would respond over to a change, as well as like play forward on longer horizons, is like predicting the weather over years, especially at like micro scale. And so it's like, is it going to rain in 7 years today? Who knows?
But this is the same problem also with verifiers in general, right? Like in some sense, if you have something like very good that you can verify your results, so you already solve most of the problem.
If you can verify it offline and if it represents the set of tasks you care about, then yes. I think finance is not one of these problems because like the states of the world are a kind of you will never be in the state you're always out of distribution, basically. There's no real world distribution. Like there is, I think the reason people find like linear methods much nicer to work with is because there it's like you can understand the feature trends much more directly. And it's less about modeling the system, and it's more about modeling features, where it's the features capture some aspect of market behavior that you can plot historically and be like, oh, this feature is actually quite stable over time. And so there is kind of a Humean induction problem where it's like, we assume it will be stable tomorrow because it's been stable in the past. But I think that tends to work well enough that it is how that industry mostly operates, as opposed to things that are very much about simulating like the behavior of what's ultimately a very complex chaotic system, where you want a simulation that can run at smaller scales, which would compress the complexity of the system by definition. I think is quite tricky to do it in a way that's allowing for full reactivity rather than just kind of trends. So yeah, RL in trading is hard. Some people are going to have to keep trying. One day maybe it'll work. But
Okay, so now you have like we understand like why to do RL and on which task. So now what are the components that we actually need in order to do it?
yes, so for LLMs to do RL, like I think the couple buckets of tasks that are the most natural for it are agentic tool use, agentic search, and agentic coding. So this would be the sorts of like basically think of like the products people use AI for that work currently are typically things where it's like an agent is going to go do multiple rounds of either tool calls to do like web search or lookup or editing of a document or like writing and running code. And these are the sorts of things where you have a very discrete environment, and you also like measuring whether they've been done correctly or not is like not that hard. Like it's hard, but it's not impossible. Like you could imagine, like think of a like deep research from OpenAI, which I think is like the first example of like agentic RL like really working at scale, where the thing that comes out is like very impressive, and the amount of like tool calls that are done, the length of the rollout to get there is quite impressive. And I think this has become like the paradigm that everyone's kind of following in lately is how do you build your own deep research for X for anything? What are the algorithms? And part of this is like it's going to be an LM. It's got to be a pretty big LM to be smart enough to do any of this at all. And you want a very high fidelity environment, which could be the real web, but it could also just be like local tools with like task responses for certain things or like simulators. There's cases where like you can have, but what you really want to be able to do is grade the final thing. And I think LLMs are smart enough nowadays and robust enough nowadays that you can start building these like reward model systems out of LLMs in ways that are like, it's a iterative process. There's a lot of engineering involved in tuning to get it right. But for example, there's a lot of questions that LLMs are very good at answering yes or no to, like, does this paragraph satisfy this property? And so this can be a yes or no question that smart enough LLMs can just answer essentially perfectly, or with a low enough error that it's essentially noise. And now you can start grading this question of like, oh, I have 20 properties I want the final output to satisfy. For a research report, does it have at least 30 citations? Do the citations like include behavior that is reflective of the initial source? And maybe you have a agent that's got to do this little verification step. But like, if the things you care about are checkable by reliable LLM systems, then you can kind of optimize against them. And so you can start optimizing a model to do something that is going to have this final output, which satisfies all these properties, because these properties are now essentially verifiable, even though they're semantic.
But do you think like there is all this debate, right? That like if we have enough information with only the final output, or like we actually need for some tasks and some problems, we need the intermediate results also, right? Like to assign information.
Yeah.
Do you
I
think
mean,
so? What's your take here? Do you think like there are problems that we actually need it, or we are good if you have enough data? The only the final
yeah.
output will be fine.
I mean, I think it's like an implementation choice. Like, for example, it's a deferred credit assignment. Like, for example, in normal RL, let's say you do, like, let's say there's a game where you have a value estimator for your internal state at a given point or just the final outcome. But like the idea would be that like these internal state value estimators are learned from essentially doing the backward induction from the final states. And you're learning like a model of the value. But like in the limit, this doesn't matter. Like in the limit, enough samples gets you all you need. And the question is, does it actually help in practice? And I think for LLM, the trend has been no so far. I think this could change as we go to longer horizon rollouts, but it's not the winning paradigm currently. Actually, I wrote a paper about arguing for it, but it's like, it's the sort of stuff that tends to just kind of become less important. It's a fix in some cases, but it doesn't feel like like a like an essential fix, especially because like for these problems, usually evaluating whether a step is good is like with some rule-based system is really hard and is going to like potentially conflict with the actual goal. And also like if the model is in this like 50% regime where it's doing well enough, you kind of have plenty of gradient to go off of. Like you could spend more compute on trying to like find more bits of signal instead of doing more rollouts. But it's the sort of thing where it's like you're spending your compute differently to do more fine-grained rewarding as opposed to doing more sampling. And if your sampling is sufficiently rich that it discovers lots of like good versus bad strategies naturally, you can kind of just like let sampling do its thing.
And what do you think about like a multi-agent system versus like more smaller, like smaller number of agents? Do you think there is like, I don't know, it's easier to do it with a multi-agent system? Do you think as we have more and more agents or tools, it will be easier to get the signal? Or you will have more noise?
So I think like if the goal is to decide whether a problem should be solved by one or many agents, it's the same sort of axis of like how big should your model be, how fast should it be, whether you want to scale like your chain of thought versus parallel. Like it's a way of exploring the boundary between like serial and parallel sampling where you could set up a system with the ability to use multiple subagents and like do RL with some like cost objective to discover the optimal like architecture potentially for a given system. But I think a lot of people are just kind of like trying stuff and seeing what works. Like question of like whether you should do multi-agent or not is a function of the goals of the system, part of which will be cost and latency. Like for example, if you had an arbitrarily long context model and you didn't care about runtime or like number of tokens burned, you can do everything with a single agent. If it was like are perfectly good at adhering to long context, because it's just like anytime I want to do a subagent, like just do it now. Then when it's done, go back to what I was doing before. And so the question is like, when should you take these things out from this like fully serial version and start parallelizing them? And it's like the parallel versions will have like less information because they can't see what the other agents are necessarily doing at the same time. If one was going to be coming later originally, but now is like happening in parallel. And this is the same with like algorithms. Like GPUs are all about optimizing like parallel processing rather than like total number of like it's less. There's certain types of patterns of optimization and of for circuits as well as for agents that can be parallelized, but some things like are very serial by nature. So like I think code-based changes are pretty serial by nature. It's like if I want to do a bunch of features, a lot of times these features are very interdependent and it's hard to like do them all unless they're very decoupled. But like for search, if I'm just trying to find information, it's much better to like maybe search 20 websites in parallel because I just care about, does this website have an answer to my question? And so I think it's a very problem dependent design choice.
And so do we have any, I don't know, theoretical results that can guide us, or we just let's try and see whatever works?
I mean, I kind of like circuit complexity here as a way of thinking about it. Like it's not about LLMs at all. It's more just about like, what is the class of problems you want to solve? Is this a problem that requires like lots of space? Is it a problem that is amenable to efficient parallelization? And so like we understand this in terms of theoretical computer science, like fairly well for like basic algorithms. And I think in my mind, there's kind of this mapping between like circuit based, like ones and zeros algorithms onto their semantic kind of counterparts. And so there's a question of like, let's say some problems are going to be more shaped like breadth first search, some are going to be more shaped like depth first search in terms of like which one is going to be a better, more efficient strategy on average for the distribution of tasks you care about. And so things that look more like breadth first search are going to be more amenable to parallelization versus things that are depth first search. You're going to need more serial like computation.
Okay. Yeah, let's talk a bit about maybe distributed environments and decentralized RL that
Yeah, in terms
you're
of like what
working
we're
on.
Yeah, so at Priminal, like what we're actually doing and building, I know we've just kind of been chatting theory for most of the time so far. Like there's a lot of focus. So we are, as a company, we are a open source research lab. We are training models and creating open source libraries and infrastructure, but we also are a compute platform. And these are kind of the direction as a company we're going is in the direction of like kind of research platform experiences for people doing reinforcement learning and agentic optimization and evaluation and deployment. And so the idea here is to really like create infrastructure that we are going to use ourselves to do research, but then also make it available to people to use on top of our compute platform. And so the Environments Hub is like a piece of this. So the Environments Hub is a open source platform layer. So we have a library called Verifiers is what I have been building over the past year. And it's a toolkit for making RL environments that you can then use for LLM reinforcement learning. The Environments Hub is a platform that allows you to kind of browse and share and use environment implementations from yourselves or other people in the community. And so we're trying to have it be like essentially a community platform for people creating RL environments as well as evals, where we kind of want it to be the sort of thing that is more than the sum of its parts, in that the benefit of having all of these in a unified format makes it easier to iterate faster. Like there's a lot of pain points in the open source ecosystem around like running different benchmarks that all have their own bespoke harnesses. And so like running a full suite of model evaluations on like, let's say 10 different agent benchmarks is like very painful currently. And so that's one of the goals, is to like have a more streamlined way of doing this by having a unified format that can allow people to plug and play, and we've been working on like sourcing implementations for most popular benchmarks in our kind of library. But also it's to start having, I think, hopefully return to the train test split era of machine learning. And I think LLMs have been in this weird spot for a while where like, we definitely don't want to train on tests, but we also have been talking about training and testing in very different ways. We're just like, part of it is that the labs who are training these models don't talk about how they're training them. And so we're like, okay, the labs are just going to go do some magic. Then we come back with a model. Then we're going to eval the model on something. But really like what we're doing is what they're doing too is they're thinking about what do they want to measure? What's the train set version of it? Training on the train set. And like, that's kind of what I think is missing out in the open is like we had this in the old machine learning days. So you have a benchmark, but you also have a train set for it. And at some point, train sets in machine learning and AI went away. And RL environments are a way of bringing them back, where there's the eval, but there's also the environment, which is your very direct way of training on it to see how well a different algorithm or a different model will perform. And it allows you to kind of just do more science around understanding what the right trade-offs here are. And I think ultimately we want this to be the sort of thing that like we're also a company, like we are building products around making this easier. Like our aim as a company is to just make it easier for people to do this research. And so we'll have more stuff coming soon that I'm quite excited about in the direction of like just more user-friendly and developer-friendly interfaces for doing this kind of stuff on top of the Environments Hub and creating but yeah, just that like I think the environments we see as like a very key piece and kind of like an abstraction layer that is very usable for lots of things, whether it's synthetic data or evals or RL, like or distillation. Like these are all things that if what you care about is training better agent models and evaluating and optimizing your agent models or prompt optimization, like the thing that you use to do this essentially is an RL environment, whether you're doing RL or not. The environment as the abstraction is an entry point into this kind of feedback loop.
Yeah, no, what I was gonna ask was, well, and I'm glad you brought up like prompt optimization. I've always had this idea that you can use, and I know there's this term like verifiable rewards, but that you could even do something almost as simple as this repeatedly prompting like make it better almost to a prompt, and maybe not like that, but especially if you did like make it better and then had test prompts or candidate things that your prompt has to succeed at doing, for example, like for classification, and you keep optimizing in a loop until it does. I'm fascinated by how little this particular technique seems to have proliferated. Maybe you would say it's proliferated a lot in research circles, but I figured that normal people would have been using this kind of thing, and I don't see it too much. I'm wondering if you have opinion.
Yeah. So I think the richest ecosystem of prompt optimizers is within DSPy.
Yes, I agree.
And I think like I'm a big fan of Omar and all the stuff he's doing there, but I think it's also the sort of thing where it's like it's a very opinionated framework. And so I think like in some ways the prompt optimization has been kind of the sort of thing that is mostly accessible out of the box if you're already building in a framework that is supportive of it. And I think it has I think we're starting to see this change now where it's becoming more of a general thing. Like the GEPA JEPA algorithm has had a lot of kind of attention. We're working on very soon. We'll have kind of native support for that in Verifiers. But I think it probably should be a primitive that people think about more, especially because like if there are good algorithms for it, it's like a worthwhile area of studying different algorithms for it. But you can also use environments to optimize your prompts. So let's say one of your fields that your target parameters are not just your model weights, but your system prompt. You can do like evolutionary prompt optimization where you are then also like the flow from like data in terms of your rollouts and rewards into your like model update, in this case being a system prompt, or like any other sort of like template that goes around your model. It's like part of the harness. It's just a different optimizer target in a sense and a different algorithm for doing optimization. But the principles of online RL are still very applicable there.
Yeah, and you made a comment also earlier talking about how like training sets kind of died out for machine learning, like that concept. I do want to point out that I learned way too much about k-fold cross-validation, given how little it's now used anywhere in machine learning. And I feel a little bit like I had my time. Not, I'm joking because I really think
Yeah.
cross-validation is a great technique. And indeed, the part of Stack Overflow that was dedicated to machine learning was called cross-validated, a good name at the time.
Mhm. It's a good name.
Yeah. And I'm just curious what your thoughts are. Is there any value in techniques like that? Do you think it'll ever come back for trying to really heavily verify the truth of, epistemological claims of, we understand things?
Yeah, I think there is definitely a place for it. I think especially in terms of I think the low-hanging fruit version that's very like important that people don't do very well right now is just like understanding confidence intervals for evals, where people report benchmarks without talking about margins of error and be like, oh, we beat that model, but it's like by 0.5% on a benchmark with like 500 samples. It's like, come on, what are we doing? What are we doing here? And like, so I think this is a way of getting more, like, there's definitely a need for more statistical rigor. I think in RL specifically, it tends to be less of a focus, partly because RL by design tends to not memorize that much and is much more about policy optimization, where like if your reward goes up and you have a holdout set from the same distribution, it's actually pretty rare in RL, especially like large scale LM RL, to see that unless there's like a true difference in distribution, that one of them is like much more performant than the other, unless you have like individual hard samples in the other one. But above a certain scale, like part of it is just that like there's been a lot of discussion about like the information you learn from a gradient of RL, and it's very sparse. And in some ways that's good because it means it's very hard to memorize. Kind of the thing that you get out of an RL gradient, one way to think about it is like, let's say you do a rollout that you're sampling tokens and most the tokens at the start are like the same for a while. And then at some point they diverge and then one goes ahead and wins, one loses. Typically this gradient will be like, oh, this token was better this way than that way. That's the one thing we can really target based on the reward signal we have. I'm going to nudge this token more in one direction than the other. And so those are the kinds of like qualitative updates you get out of doing RL for LLMs, which are not that, if you have enough samples, if you have enough like initial data, like it's pretty hard to memorize. And so I think it's like a little less of I think pre-training is very important. SFT, it's still pretty important. RL, I think it's good to measure out of sample on a different holdout task, like a different eval. But generally, if you have a split for one environment, you're going to not see too much difference between the in-sample and out-of-sample.
I have a question. So, how do you see the future of RL, like in general, in specific RL, or like in general, all the training pipeline, if you want? Do you think like we will still see very specific, pre-training, mid-training, post-training with SFT, RL, and like all the others, or do you think like we will see kind of like we saw several works like that, right? That like try to do more well at the beginning and like try kind of combination. Well, what do you think we will
Yeah, so
see?
I'm admittedly fairly skeptical about RL going all the way down to the beginning of pre-training. Like I think that's kind of what we were doing in the 2010s, is we were doing pre-training RL. It was all RL. And we did it, and it's like, it doesn't actually work that well. But the thing I think is most likely to really change is seeing mid-training and synthetic data get pushed further into pre-training, where I think we definitely have started to hit limits of like raw web text, but also a lot of that web text data is like pretty bad. And so there's a lot of very low information density data that comes out of web text. And so I think there's a lot of interesting research around, if you're going to be spending the compute, you might as well have better data for it. And like, what are the ways of kind of creating like large scale mid training data sets that are going to give you the right priors for doing RL or other kinds of sampling, which is still like a very open and interesting area of research. So there's a cool Pierre-Carl Langlais or Doria Alexander on X has a great release from a week or so ago. Baguettatron and Monad are these two tiny models. It's 50 million parameters and 300 million parameters that are trained on like very little data, like 200 billion tokens of a very specific synthetic data recipe. And what comes out are very viable language models that they're small, but they kind of feel like your typical like D2B language models. And it's like, these are the sorts of things that you could run on a phone and like use for autocomplete or like action prediction, like summarization, totally fine. But they're also reasoning models by design, because their whole data set is like mid-training for like baby reasoning. And there's a lot of interesting data design choices about how you curate this data. And it's like these models have been trained on, like the starting seed was like 50,000 Wikipedia pages and then lots of synthesis on top of these Wikipedia pages using LLMs. And so you need some world knowledge, but you don't need all the world knowledge. And you definitely don't need like all the HTML of the web. And so I think there's ways of being much more targeted about what information do we want in these models and what is the right way of representing this information, taking like a web page or a piece of code or a GitHub repo and really expanding it into a much larger, richer mid-training data set that gives better priors for the sorts of things you want to do with it later on, rather than just like training on the direct tokens themselves.
And do you think like I will be, I don't know, for smaller models, for example, like, do you think like we'll see more RL training, or like we'll see some other methods that will be better?
I think it comes down to what's the prior. I think historically, over the past year or so, people have generally found that RL works better on bigger models. I don't know that this is like a law of nature, though. I think it's more of just what happens in these models, where like the sorts of things that bigger models can afford to represent or end up representing based on pre-training happen to be useful for a better sampling distribution. And so I think this question of like, how do you use mid-training to create better priors for RL on small models is like a very open area of research, and also a pretty accessible one. Like the total pre-trained costs for those ones that this guy did were like a few thousand GPU hours. It's the sort of stuff that like researchers could do outside of big labs on like much more academic like research budgets. And I think is a lot of open questions there about recipes for data that are then useful for downstream RL.
And what about multiple problems? Like, do you think like we will see specific models for each problem, or like one model that can solve multiple problems? And if yes, if so, then like what, you will train the RL on each one of the
Right.
problems?
Yes, great question. And I think from like a practical perspective, there seems to be a lot of interest in and momentum towards application specific RL, where you can think of the any given like AI product that's going to be given to an end user as a distribution of tasks from the user as well as an environment. And so I think like the Cursor Composer release is really exciting to see, because that's like, to me, that is like the sort of thing that we want to have more people be doing, is like, how do you create an ecosystem where the ability, where part of the design process of building an AI application is you think about the tasks it should be doing. You think about how you'll measure how it's doing well in the same way that you do for prompt optimization or model selection. But then once you do this, you also have the ability to optimize this end to end, to have a smaller, more efficient model, a more cost-effective model really become excellent at the thing you care about, rather than just like hoping that the generic big model was trained in a close enough thing that it does well on it. And so like, I think that's the mission really, is just like, and it'll depend on like how broad is this task set, how complex is the harness, how like what scale of inference volume are you operating? Can you amortize out the cost of doing RL across this set of tasks? And so I think like there's this Pareto curve of like cost, speed, generality of the thing you care about, but it's very much I think there's a lot of these settings where the Pareto optimal thing will be to like do RL on a like really good starting model, really optimize it for the use case you care about, and then amortize this initial like compute of doing the RL across the like improved cost of inference relative to like a larger, more expensive model without domain-specific post-training.
Okay, I have one more question. It's not really related, but so there are all these papers a few months ago about random verifiers, right? Or like learning from one example, and like a series of works that had these weird results that measured entropy and all these things, and found really weird things. What's your take from these
Yeah.
works?
I think the easiest story is that like a lot of these models are trained on data that whether it's the actual problems themselves, it is like so much math data that you end up covering a lot of these problems. And the base models are still like base models in general tend to be like kind of random and they're not necessarily the most like sharp in their distributions. And so there's a sense in which like for example, you can simulate this by like doing beam search, but also what you're doing with RL, especially if you're doing things like a KL penalty or some objectives for RL have like implicit favoring of kind of the most likely examples, regardless of whether or not your rewards are random. And so you could think of some kind of contrived or like broken RL setups as like just mode collapse. And I think if you have a model that's been heavily pre-trained or mid-trained on like math data, and you're looking at math benchmarks, and you have an optimizer whose sole goal is just like mode collapse or like lower the temperature, or like mode collapse on a sequence level sense, then it's not that surprising to me that like this just makes models better. But I think it's kind of a red herring about how to think about RL more broadly. Other than that, like you want like RL really is going to be like in some ways all optimization is about shrinking the distribution. Like sometimes you have to change it, but like the initial distribution of like a randomly initialized LLM is going to be like any token. And so pre-training is like mode collapse towards natural language, away from gibberish. And if RL is like further mode collapse towards like correct answers, and you can kind of calibrate like which answers are correct and collapse in this direction, you still want like exploration. So there's a lot of work on like how do you avoid like full entropy collapse so that your model kind of so the temperature becomes meaningless. But it is nudging the distribution in different directions, and you want this to be in a direction of like better answers.
Yeah, I like to think about it as compression, but this is only my perspective all the time. Okay, cool. Maybe let's go to some questions from the audience and from Twitter and LinkedIn. Okay, I would like to know about concrete examples of agent workflows that customers come to them with. The bottlenecks they face doing evals and RL for them and how they overcame.
Yeah, great question. And I think like a lot of the tasks that are really ripe for this stuff right now are in the regime of like agentic tool calling and agentic search. So like searching over your documents, searching over your internal code base, having models calling tools that are like internal MCP servers, I think is the category of stuff where people are like I think the people who are the best, like most ready users of RL are people who are already pretty comfortable building agents and already relatively comfortable doing evals for their existing systems. And so if you know how to use like LM judges for your prompts, for evaluating whether to use GPT-5 or Claude for a system, I think this is kind of the right starting point. So if you built an agent that is using, let's say, GPT-5 or Claude, and you are able to tell whether or not one or the other is better for your system without just like vibe checks, I think now this is the starting point where like doing RL is like quite accessible. Or at least that is our goal, is to make this quite accessible.
Okay, next one is what is the current main goal of Prime RL as a framework? And how would he rank the different trade-off they are making?
Yeah, so Prime RL is very much like our core research repo. And so like there's some things that are like we do want it to be user friendly, but it's also like it's not gonna be everything for everybody. And so for us, the important thing is that we want it to be like high quality code. We want it to be very scalable and performant code. And we want to like synthesize what we see as like the best practices from the research literature. And we'll have like some flexibility, but we also like don't want to, there's a lot of things that like features that supporting them would make the code worse and would make it harder to maintain. And we also don't think that's a feature that is actually a good feature. And so in that case, we're just not going to support it. Like, for example, we are kind of the mind that like doing synchronous on policy RL is like actually a bad idea. Like,
Why?
so we'd fully do because you can't, if you care about horizon length, if you care about like agentic
Maybe
rollouts,
just a word, what does it mean? Synchronize
yeah,
off
so
policy. Let's
so
start with
one
that.
way of doing RL that is a common choice of many frameworks is you have a single set of GPUs they switch back and forth between doing training and inference. So they like co-located training and inference is one term, where you train on a batch, then you switch to inference, you do inference, and your memory is swapping back and forth. And so this is like, one is that the system design of doing this memory swapping for within the same GPU like adds a lot of complexity, but also it means that you can't do both at the same time. And often once you're doing lots of rollouts, especially once you're doing longer horizon rollouts, you're going to be blocked waiting for your slowest rollout to finish. And so as soon as you have like non-trivial variance in your rollout time, then this kind of becomes a problem because you have a lot of dead time where your GPUs are just idling because you can't train until the batch is done, but the batch isn't done yet. And so what we think people should be doing is you have training and you have inference, and they're both going constantly. And you kind of update the weights for the inference workers as you can, but you still want to have this mandate of like ensuring that all of your systems are like working at full speed the whole time, as well as allowing for rollouts to potentially take much longer. And so this is where like async or off policy RL comes in, is that you might have rollouts that the time to finish one rollout is like the same time as like many full training steps, in which case this rollout will end up being trained on like later versus the policy model when it starts. So like there's this mismatch between the step of the trainer you're on and the step of the inference work you're on. And we kind of see this as like a bullet you have to bite. And so we've designed PrimeRL around that assumption. And it's one that like, I think other people have been moving this direction as well. Like I think it seems to have been a fairly validated bet, especially in terms of like what large scale systems are going to look like. But it's also like the wall clock time of if you have long rollouts and you want to do many steps of RL, you don't want to be bottlenecked by like rollout time times number of steps. You want to be bottlenecked by like training step time times number of steps, because training step time is you can parallelize along the sequence length, which you cannot for inference. And so that's kind of the main reason.
You started to say that like, okay, you don't want to allow it. So
The way you would build your system, the architecture is very different. So we don't support having the same GPU memory swap between inference and training because we think you shouldn't, but also like it's annoying to do it and it makes the whole thing ugly and harder to maintain and add more features to. And so like I think we've intended for it to be a very powerful framework and a very opinionated framework where like we're going to like look at all of the papers that come out and read what changes they make. We'll try different ones out and test them and do ablations. And then whichever ones seem to work best, we'll have those be the new defaults. And so the defaults will like kind of evolve as the research literature evolves and as our experimentation evolves. And we're not kind of promising backward compatibility with all the old features. And so we think of it as more, it's very much a framework, and PrimeRL is a framework and not a library, similar to like Torque Titan or like I think Veril to some extent, but I think Veril in our view is like trying to do so many things at once that it's a little tricky to do them all really well. And PrimeRL is going to try to do less things and just do them really well.
And what's your take on a open source versus closed source, both models and frameworks?
Yeah. I mean, I think open models are like really great. Like Kimi K2 is like one of the best models in the world, open or closed. And I think we kind of, the recipes of how to do it are like kind of sufficiently out there such that like, I think open source is very viable, especially if you have good ecosystems that grow around it and allow people to like take advantage of these models. And like, but really the wins of open source come not just from being able to see the model and understand it, but also to be able to change it in new ways and the ability to like post-train these models, the ability to optimize them for the use case, to like have more hackability, to customize things for the end users is really like where the wins come from. And cost effectiveness of really optimizing your inference for a certain model, for a certain type of workload. And so I see that as kind of like the goal of what we're trying to enable. And then I think the framework versus library split, like Verifiers is a library. So Verifiers is really where we kind of think a lot of people will want to do their customizations at the environment level, as well as around like coming up with different reward strategies. And so anything that kind of can be done at the environment level, you have a lot of algorithms, like the way you'd implement them actually is at the environment level, not at the trainer level. And so like we do want people to have very much like a space for changing things, but there's also stuff where it's like, for example, orchestrating the way that your rollouts are going to be sent to the trainer as you're broadcasting weight updates is definitely more the sort of thing that's like, it's a very hard system challenge to get it right. And once you do get it right, you kind of don't want to break it. And so I think it's tricky to have like a large number of knobs exposing many different algorithmic choices at the RL trainer level in terms of systems orchestration. And so we've tended to be more of the mind of like the systems orchestration piece is really what we want to kind of have more frozen and more of a moving target based on evolving best practices. And the like task level, dataset level, environment level, reward level changes are where we want to kind of expose more like library-like primitives to the user to really customize stuff.
Okay, final question. Do you have a plan for daily learning and improving knowledge, your knowledge and skills? What is how you are doing it?
I read the timeline. I see what people are talking about. I look at what papers are coming up. I'm in some Discord servers, and we have our internal group team channels for sharing papers that we think are cool, but really just like engaging with the research community and going to conferences and listening to talks, just trying to stay on top of everything has been the way that I also just like building stuff, like have an idea that you think maybe is doable and just like go build it. And you get a lot of feeling for like what does and doesn't work from actually doing stuff in practice.
Advices. Okay, I think we finished. Will, thank you so much. Do you have anything to add that you want to say?
Check out the Environments Hub, check out Verifiers library, check out PrimeRL. We're trying to just make it easier for people to do research on this stuff and have fun like building environments and doing training. And yeah.
Thank you so much.
Also, we're hiring too. Yes. So we are, if any of this stuff sounds fun, we're hiring quite aggressively. And yeah.
Wow. Yeah.
In San Francisco, in New York?
Mostly San Francisco. I think some roles are definitely much like very remote flexible too. And for the right people, especially.
Yeah. And I really like the Verifiers library. Very cool.
Nice. Thanks.
Thank you so much.
Cool. See you.
Bye-bye.